G'day, welcome to part 2 of the section about function inverses. In this section we're going to consider a more interesting example, and that example is going to be the function y that has domain the real numbers, and it sends the real numbers to 0, infinity. That's everything greater than or equal to 0, every real number greater than or equal to 0. And our function y is an old favorite, y of x equals x squared. So we square x. And now we're going to go ahead and graph this real quick. Should know the graph of this one pretty much off by heart by now. Here's our x-axis, here's our y-axis, and we know that the graph looks something like this. It's kind of curved, and that should go through the point 0, 0 right there. Okay, so is this function invertible? The answer is absolutely no, because the inverse should take all of the functions in the range and send them back to the one point in the domain that they came from. But if we take, for example, y equals 4, well, we know that there are actually 2 points that are sent to y equals 4. These 2 points are x equals -2 and x equals 2. So that is a problem. But it is easy to fix if we really desperately want to invert this function. And the way we're going to fix it is we're going to modify the domain. We're going to change the domain to 0, infinity as well. The interval from 0 to infinity. Infinity not included, obviously, because it's not a number. So our domain is actually now just all of the numbers greater than or equal to 0. So that means this part of the function, is no longer relevant. We don't need that part anymore. So that's our new function. Y actually takes the interval from 0 to infinity, all real numbers greater than or equal to 0, and sends it to all real numbers greater than or equal to 0, and it just squares them. Let me draw a new diagram, because that one's getting a bit messy. So our function y takes 0, infinity to 0, infinity, and it's defined by y of x equals x squared, and its graph looks like this. I don't really know why I included the other half. I didn't need to. Okay, so this function is invertible now, and what we'll notice is that so y of x equals x squared, this tells us that actually x is equal to the square root of y of x, because all the numbers we're dealing with are positive now, so we can just take the square root of both sides. So if we want to send y of x back to x, we should take the square root of y of x. In other words, our inverse function, whatever we put into our inverse function, we should square root it. And that means that y inverse of x is equal to the square root of x. Now, the square root of x looks something like this when we graph it. Square root of x looks something like that. So this is the function y inverse of x equals square root of x. And of course, this one in black is the function y of x equals x squared. Now we're going to draw the line. Y equals x. You'll see why in a second. So this is the line y equals x. Notice something odd about this. These two functions, this y of x equals x squared and y inverse of x equals square root of x, these two are actually reflections of each other. About the line y equals x. If I was to put a giant mirror along this line, I would get a mirror image, and it would look exactly like this. So these two functions are actually reflections of each other about the line y equals x. Why on earth is that? Why does that make sense? Well, actually, imagine that we were going to reflect the entire xy plane about the line y equals x. What would happen? Well, we would basically just kind of flip everything up this way. Imagine just turning this over, but we can still see everything. It's not like it's hidden by the back of a page or anything. Imagine turning everything over, but we can still see the axes as we turn. Well, that's just going to pretty much result in everything being the same, except the only difference is this y-axis will become the x-axis, and this x-axis will become the y-axis. That's going to be the only difference. And so what that's going to do is actually change these things around. This is going to be, well, this function here is going to be x equals y squared. In other words, y equals square root of x. And this function down here is going to be, well, y equals square root of x. In other words, x equals y squared. Sorry, x equals square root of y, rather. So this function here is going to be x equals square root of y. In other words, y equals x squared. So what's going to happen is these two functions have been actually flipped up the other way. They're still the same function, but they've just been flipped up. They've sort of traded places, if you will. The two functions have traded places. And so given our x-axis is up here, if we're still going to keep these as the inputs, this function now takes the role of the inverse. And if y is down here, if we're going to keep that as the outputs, this function here takes the role of the original function itself. So it makes sense for these two functions to be reflected about the line y equals x, because if we reflect the entire plane, it's basically just swapping the x and y axes. And that's pretty much what we do when we take inverses of functions, because the things going into the inverse function were actually the things that came out of the original function to begin with. So yeah, that's why that happens. And there's nothing special about the function y of x equals x squared in this case. This works for any function that has an inverse, any invertible function, which means it has to be one-to-one. So for any invertible function that has an inverse, when you draw its graph, the graph of its inverse is going to be a reflection about the line y equals x. So that is a pretty important detail. Okay, that's it. Thanks very much for watching. Don't forget to check out the notes on this section and do the exercises at the back. It will help you understand the topic a whole lot more. Thanks very much. Take care. Bye.